In this video, we just look at a general type of op-amp problem. This op-amp circuit doesn't serve any particular application as far as I'm aware of, but some of the homework problems are like this, and they're pretty much purely academic exercises, but it's a good chance to review some of the basic fundamentals of op-amps and also of your circuit theory. So in this problem, we want to find what this current is that's flowing from our 12 volt source. And you can see that there's two feedback paths, a 6 ohm between the output, here's V0 here, and the non-inverting input, and then a 3 ohm resistor in the feedback between V out and the inverting input. And then also we have this 2 ohm resistor, as you see, from this node with the 3 ohm and the inverting input to ground. So when you're doing problems like this, you always want to start off with that when you have feedback. Okay, so remember, feedback is any sort of path between the output and either of the inputs, and here we have two feedback paths. So anytime you have feedback, you have a virtual short, so the current at the input of the ideal op-amp is 0, and also the voltage across the inputs. So you see at both these inputs, we can write that the current is 0, and then this voltage here is VI. That's the voltage across the inputs of the op-amp. So you see, this is where you want to start your analysis. And specifically, remember what it tells us. When you have 0 volts across something, it means that the voltage is the same on both sides of that something. So because ideally there's 0 volts across these two inputs, that means both inputs have the same voltage. And this one here, your non-inverting input, is connected right to 12 volts. So you see there's 12 volts at this node with respect to ground, which also means that there's 12 volts at the node where the inverting input is connected. So you see this node right here has 12 volts. Okay, well now you know the voltage across this 2 ohm resistor. Since there's 12 volts on the right side and ground on the other side, there's 12 volts across that 2 ohm resistor, which means that current is flowing just like this, right? That we have 6 amps of current, right? Because current's going to flow from the higher end to the lower end through a resistor. So that's why we know the current's going right to left, and 6 amps is the 12 volts divided by the 2 ohms. Okay, just from Ohm's law. All right, now if we apply KCL to this node right here, well, there's 6 amps flowing out. There's 0 amps here at the inverting input. So that must mean that this 6 amps is all flowing through the 3 ohm resistor. Since there's 0 amps flowing to the op-amp, essentially the 2 and the 3, they're in series. They're sharing the same current. So the higher end of the voltage across the 3 ohm is going to be on the right side where the 6 amps enters, and then using Ohm's law, we can get that the voltage across any resistor is just R times I. So the voltage across this 3 ohm is just going to be 18 volts, right? 3 times 6. Okay, and now we can solve for V out. Okay, the voltage at this node here where our output is, all we have to do is sum these two voltages. That starting from ground and going this path to where node V0 is, I go up 12 volts, then I go up another 18 volts. So V0 is just 12 plus 18, 30 volts. Okay, so now we know the voltage here with respect to ground is 30. We said earlier the voltage at this node is 12 volts, right? Because there's just the plus side of this 12 volt source connected here and the other side's ground, so We have 12 volts on this side of the 6 ohm resistor. So 30 volts here. And 12 volts here. So the current's flowing like this. And that current is going to be, we can write it over here, that's going to be 30 minus 12 over 6, so 3 amps. Okay, so now at this node, there's 0 current here at the non-inverting input of the op amp. There's 3 amps flowing in, and then we have our I defined as flowing in from our 12 volt source. So I's got to be the same magnitude as this 3 amps, but really this current is flowing the other direction, right? Since this current's flowing in, this current I has to be flowing out, and our answer is that I must be minus 3 amps. Now, a question that often comes up in a problem like this is, well, how can this source be absorbing power, right? Because since this current's really going the other way, it's flowing into the higher end of the voltage of this 12 volt source, meaning that it's absorbing power. You know, because a student, you know, sometimes they'll look at this and say, well, that's the only source we have. Everything else is resistance, and, you know, we have this op amp. But don't forget that this op amp is being powered by 2 sources, right? You got plus V and minus V, 2 DC sources powering this transistor circuit that makes up the op amp. So this source can be absorbing because these sources here can be doing the supplying. So don't forget that even if it's not shown explicitly on the diagram, you do have 2 power sources here giving the op amp power.